Hello everyone. Today we had our first session in our study group. I had some feelings regarding how should we approach. I could have written my ideas or my thoughts in the chat group or in this Slack channel, but I thought it was easier for me to express my ideas or thoughts by speaking. So that's why I'm making these videos, making this particular video. Uh, we're going to study quantum computation and quantum information from the classic textbook written by Nielsen and Chuang. I think it's the right choice because a few months back, I also asked my professor, who is an expert in this particular field, and he also recommended me this book. So I think we have the right choice of textbook. Even I believe we have the right choice of chapter to begin with, because we are going to start with the chapter 2, which deals with quantum mechanics. So we are studying quantum computation and quantum information, and all the ideas in this particular field are based on the principles of quantum mechanics. So beginning with quantum mechanics, yeah, it's the right choice. But I have my feelings. How should we approach? We have people from different backgrounds. We have people from physics background, we have people from engineering subjects, even we have people from the business world. I mean, they run quantum business, but they also want to understand what's going on, or what are the technical details in the field of quantum computation and quantum information overall. So we have people from different backgrounds. So it's our decision how should we approach our studies. So I think chapter 2 is the most important chapter in this particular book. I believe once you understand uh, all the topics from this chapter, you can easily understand the rest of the book, or at least you can proceed first once you get a solid grounding in the chapter 2. So it's very important to spend a significant amount of time in this particular chapter. That's my realization. So that's the only message I wanted to tell. But I have some feelings after the completion of my first reading of this second chapter. Even though I haven't studied all the topics, and even though I haven't understood all the topics, but I have some feelings. The second chapter deals with linear algebra and introduction of quantum mechanics. And in the later sections, they have some specialized topics. In the last section, they have EPR and Pale inequality. So it's a compact chapter. To be honest, the linear algebra is itself a particular subject, and in conventional curriculum, they spend a whole semester to study linear algebra. So and then we have quantum mechanics. So it's really a compact chapter. So I think we should spend significant amount of time to study all of these. At least it's worth studying. Why linear algebra in the first section? Because the whole quantum mechanics is written on the language of linear algebra. In quantum mechanics, we deal with quantum states. These quantum states live in Hilbert space. Hilbert space is a vector space, and we perform quantum operations in the name of quantum operators. We imply these quantum operators in these quantum states. We get eigenvalues. We do quantum measurement, and all these natural phenomena are written in the language of linear algebra. So to understand linear algebra is very important. And then in the second section, they talked about quantum postulates, a basic introduction to quantum mechanics. They talked about states. They talked about state space, actually, and how these states is evaluated over time. How Schrodinger equation, unitary operators govern the evaluation of these states. What do you mean by quantum measurement? So these are the topics, also the postulates of quantum mechanics. And then we have two particular topic called positive measurements and POVM measurement, positive operator valued measure. These are two special topics that will be necessary in the upcoming chapters, I believe. And let me give you an example how these sections are interconnected. Here they talked about composite systems. To understand composite system, you need to understand tensor products. What is composite system? Let's say we have system in Alice's side, system A, and we have system in Bob's side, and this is system B. But we have the composite system, and we have to take uh, the tensor product of this individual system spaces, and then we get the overall joint system. And how do we do this? We know this particular thing in the section, tensor products. So once you understand tensor product, you can understand composite system. But there is another topic called entanglement. To understand entanglement, you need to understand what is composite system. Uh, and quantum entanglement is very important to understand some crypto protocol or other protocols in quantum information and quantum communication. And this is one of the most important topics, quantum entanglement. And to understand quantum entanglement, you need composite system. To understand composite system, you need to understand tensor products. So all these things are interconnected. So see how important is this chapter. So I think we need to spend a good amount of time. In the last section, they talked about EPR, but before that, they talked about density operator. Density operator formalism of quantum mechanics is maybe some quite unusual to somebody, some of us. At least it was for me in the beginning when I studied quantum mechanics for the first time. I studied about quantum states, but there are some other ways to express to state. So density operator is a way. So it's also important to understand density operator. And then lastly, we have the EPR, the famous Einstein-Podolsky and Rosen paper, where they questioned the completeness of quantum mechanics, and they have their argument, some valid questions regarding the completeness of quantum mechanics and the Bell inequality. And this Bell inequality, the contextuality of quantum mechanics, how quantum mechanics is different than the classical perception, and how quantum mechanics is non-local. And this Bell inequality is the measure of non-locality, or the boundary of non-locality, I would say, uh, uh, or locality, I'd say. Our classical world is local, at least we have this perception, but our quantum world is non-local. So from this Bell inequality, we get this perception. So if you don't have your introduction in this field, you need some time to understand all these topics. That's what I want to say. Maybe I am oversimplifying all these topics, and oversimplification can arise confusion. I don't want to do that, but what I want to say that we need to spend a significant amount of time in this particular chapter. Linear algebra, it's itself a subject. Quantum mechanics, it's a huge subject. And then all this basic introduction to the field of quantum computation and quantum information, like density operator, formalism, this EPR and Bell inequality, all these stuffs are very important, and it takes time. So even we sit twice in a week, and if we spend 2 months in this particular chapter, I think it's worth spending. That's what I wanted to say. I could have written all these things in the chat group, but I think it's easier to speak with you guys. So that's why I made this short video to convey my message to you. But it's your decision. How should you approach? If you want to go fast, you can go fast. If you want to go slow, build from the scratch, then you can go slow. It's your decision, but I just conveyed my message. I have some feelings after the first reading of this second chapter. That's what I wanted to say in this video. Thanks. See you soon.